Okay, so we're talking about redox again, and there's a reason for that. And I was talking yesterday about oxidizers, okay, strong oxidizers. Obviously, redox reactions are a transfer of electrons. And we've been through redox once before, and we're going to go through it again with a different perspective. And identifying a redox reaction, one easy way in AP chemistry when they start getting advanced is looking for oxidizers. Oxidizers are oxidizing agents, and I call them electron sinks. And we use these specifically, okay, to drive chemical reactions. Just like strong acids drove weak acids to completion, strong oxidizing agents can drive elements that aren't very good or compounds at losing electrons. It can force the transfer. Okay, and we know when it comes to redox, we know spontaneity occurs due to a positive voltage. Meaning, if Mn plus 7 is the heat sink, and by the way, this is, the electron sink that we're going to use today in our lab, into the lab, okay, Mn, or the manganese ion in the permanganate ion, it's KMnO4, K is plus 1, dissociates into a spectator, and we're left with MnO4 negative. That means that manganese is plus 7. To become plus 7, you had to lose 7 electrons. And when you lose electrons, the remaining electrons feel the nucleus more. So this thing is really small, and it's plus 7, highly attractive coulomically to negative electrons. And then on top of that, you have these oxygens, which are very electronegative. Electronegative means you attract other chemicals' electrons. Why? Well, oxygen has a lot of protons, okay, in its same energy level. We talked about it. Great ability. So this thing loves to pull electrons. And it's got a high, very high positive reduction potential to drive something that could be negative as it oxidizes, and as easier a cell would be positive. So there are some important parallels, and you should always ask your teacher, why are we doing this now? Not because it's on the test, not because it's part of the curriculum. I've got to interconnect this, and there's a reason that I'm bringing back redox. And the reason is we use redox the same way we use acid-base reactions or acid-base titrations to find something about an unknown. In the case of acid-base reactions, we were finding the concentration of the acid, we were finding the concentration possibly of the base, we were finding the active ingredient in Tums, we were finding the active ingredient in Bayer. All these things we do by using some known concentration to figure out some unknown. That's essentially what titration is. So I'm bringing back redox because guess what? They are redox titrations. We saw redox in terms of voltaic cells. We saw redox in terms of electrolytic cells. Those are applications, very important applications. But now, another important application is if something's not an acid or base, maybe I can force it to give up its electrons if I force the reaction with a strong oxidizing agent. So we're going to do a volumetric titration. So if something's not an acid or base, how could I evaluate its content? Well, I could have it lose some electrons if I pair it with something strong enough to force the action to go to completion and do stoichiometry. The only difference here, party people, is that the stoichiometry isn't 1H plus to 1 hydroxide. The stoichiometry is the moles of electrons lost from the analyte is going to equal the moles of electrons gained by the titrant, okay? And there's some other differences here. So that's where we're headed. That's why I'm bringing back redox again. And again, I think that's the best way to learn is to keep seeing it from different perspectives. So we're going to do analytical chemistry, not acid-base chemistry, but do volumetric titration. And I'll tell you how we can get to the endpoint or the equivalence point without acid-base indicators. Okay, so that's what yesterday was about, okay? And so today I'm going to go further, okay, a little bit. All right, and I want to bring back, okay, our net potentials again, okay? Okay, so yesterday I showed you something called Table J, and I do so not because it's an AP-based table. We're going to take the regions in this, and they don't use net potentials. It's by far the worst table there is known to man, in my opinion, but we have to work with it. Okay, so before I do that, I definitely want to keep understanding how the net potential table was built. So I'm going to go to my iPad here, and I'm going to be cursoring, so excuse me. All right, and when I do so, I want to pull up the net potential table. Okay. Now, so there's my net potential table. We've been using it all year, except now, the one I'm making you use, I've added some strong oxidizing agents. How do I know? A lot of oxygen surrounding something positive. Hey, there's the permanganate ion that we're going to use. Hey, there's the dichromate ion. Here's the nitrate ion. We talked about those yesterday. The nitrate ion, potassium nitrate, saltpeter, gunpowder, explosives. These things can be particularly very dangerous. And look at their positive potential, their positive reduction potential. This is really important because if I'm really positive in my reduction potential, I can force something to oxidize that's very negative. Okay? Case in point, all right, theoretically, hydrogen peroxide is positive 1.78. Gold, which is one of the metals that really resists oxidation. That's why it stays shiny. That's why we think it was the first metal discovered, because they start probably glimmering in a river. Hey, why does it glimmer? It doesn't oxidize. So gold resists oxidation. It's negative 1.50. But this guy can drive it to oxidize, okay? And that's the point I'm trying to make. But, all right, why do we have this standard reduction potential? What is so special about this zero? Are there no real volts or flow of electrons here in this half reaction? What's happening here? Why is it zero?
It goes back and forth.
Right, this is what we call the standard cell. To find these voltages, you can't really find a reduction potential without something oxidizing. So they used either this forward direction or reverse direction to get these voltages. It's called the standard cell experiment. I know I mentioned it yesterday, but I'm going to mention it again because I want you to understand where this comes from. So the standard cell experiment looks like this, okay? So they have, and I know you were home with it, but I know you guys at home saw it, but I just want you to understand where it comes from. Okay, so first and foremost, I'm pumping hydrogen gas into this container. And the molarity of the hydrogen gas is, the pressure is 1.0 atmosphere. These are standard conditions. And then I have H pluses in here, 1.0 molar, okay? Then I have a sealed electrode. And then over here is the test cells, okay? And what we set up is we set up a wire that goes to a voltmeter. Now the voltmeter, as you did in your lab, has positives and negatives to it. So if I make the negative go here and the positive here, okay, it's going to read the voltage if this is the anode and this is the cathode. Okay, very important you understand this experiment. Okay, now the test is over here. Okay, so like I said before, and I'll use a different one, what if I had zinc metal here? And we always pair it with its ion, because you don't know if the ion is going to get reduced or the metal is going to oxidize. I mean, we know the answer here, but here's zinc plus 2. Okay, now we set the experiment up, okay? And it just so happens that the H plus is a strong enough oxidizing agent, okay, to pull charge this way, okay? Now, if it pulls charge this way, that means the zinc is going to oxidize, becomes zinc plus 2 and 2 electrons. The 2 electrons are flowing here. Hey, okay, the H plus is grabbing those electrons. So the 2 H pluses grab 2 electrons and hydrogen gas is made. You have to know if hydrogen gas made when in the presence of protons. And this is a spontaneous process. Electrons are flowing in the opposite direction than expected. I don't flip my voltmeter, I keep it that way. And so because I expected my anode to be here, and now the anode is here, what I have is voltages that are negative. Now I know it's a spontaneous process, but I set the voltage meter this way for a reason. Okay, so my voltage meter goes negative, or if it's a digital, it's negative 0.76. It's really a positive change, but that's the way I set my voltmeter up. And so we write the voltage for zinc to be negative 0.76. That's the way we did this experiment. Okay, now, what if I change this to copper? This is copper and copper plus 2, and I could put copper plus 1 there. Okay, same experiment. Except this time, the H plus is not strong enough as an oxidizing agent to rip electrons from copper. Okay? So that doesn't happen. In fact, it's the copper plus 2 that's a stronger oxidizing agent than the H plus. So electrons travel this way. It's the copper plus 2 who now pulls electrons through. So the copper plus 2 grabs the 2 electrons and becomes pure copper. Who does it grab it from? Can't grab it from the H plus, it grabs it from the hydrogen. So the hydrogen gets oxidized into 2 electrons and makes 2 H pluses, right? And this is a spontaneous process. But I got electrons going where? Okay, this way. Hey, H2 is losing electrons. That's where the anode's expected to be. And I get, in this case, because the voltmeter is still set up that way, positive 0.36. And that's how this was built. I know I made you do this many times. Positive 0.34. We got it. I'm a loser. Okay. So that's the experiment. So copper plus 2 was not a strong enough oxidizing agent. I'm sorry, the H plus wasn't a strong enough oxidizing agent to rip electrons from the copper. And you can see that because copper going this way would be negative 0.34. So as you can see, the higher you go up on this chart, the more positive your reduction potential is. If you're an oxidizing agent, it's your ability to get reduced. You pull electrons from things. So as I said before, who is the best on this chart? Fluorine is the best at grabbing electrons from things. If we're in a fluorine environment, we're all dead. Okay, electron transport chain. Remember, we had a set of what? Proteins. Okay, and electrons are carried through these chain to push protons through. The final acceptor is O2 to make water. Well, if we've got fluorine in our system, it would yank them immediately. They would never go through the chain. We don't make energy, and we're dead. Okay? Or we would evolve. But look at these guys. So the ability of these guys to rip electron from things steadily increases. So one way to look at this table is anything on the top is a strong enough oxidizing agent to rip electrons from these things going in the reverse. And the positives and negatives work out. Fluorine being positive 2.87 can overcome a negative 1.82 this way. So everything here can react to anything below it. And if you look, based on our chart, look where hydrogen is. Look what the proton, I should say. So if you think about it, if you do the math, it is only strong enough to rip electrons from these metals. So you need to know, okay, for the AP, when, or we call it a reactivity series, how can free protons produce hydrogen gas? Okay, they can only react with these metals. And given net potentials, you would know that, okay? All right, so how do we use this chart here? Table J, can't stand it, but there it is. Table J in all of its glory. Here's what they do. Instead of using net potential tables, they say the activity series of metals. Metals are the big guys, they lose electrons. Some lose better than others. Some oxidize better than others. They put the ones that are best at oxidizing. Look where lithium is. Where's the best element that oxidizes on this table? On the bottom right. Look at its oxidation potential. It would be what? 3.05. So what they're doing is building a list in reverse. Okay? Notice lithium. Who is the metal that, and on this list, this is not the complete list. If I take out the CRC Bible of chemistry, let me hear angelic sounds. Oh. Okay? There's about 20 pages long list on very small writing. Okay? Upside down. All right? Of this table. So there's a lot more to it than this. This is an abbreviated table. Okay? So in any case, all right, who on this list is what metal on this list is the worst at oxidizing?
Cobalt.
Well, not cobalt, solid metal.
Gold.
Yeah, gold. Gold reduces oxidation. That's why we put it on connectors and electronic equipment. We know it's not going to rust in the presence of normal compounds. Okay? And of course, that's why everyone loves gold. It stays shiny. It keeps its luster. Okay? So if you look at this list, going in reverse, who's on the bottom? Gold. Who's second? Silver. Look at this list. Hey, who's on top? Gold. Eventually we find our silver. Gold, by the way, Latin for aurum, sun. Okay? And of course, argentum is Latin for silver. So if you look at the list, hey, gold, okay, silver, copper, lead, and we go to this list, gold, silver, copper, lead. Now, what's confusing for the Regents level student who never looks at a net potential table is they write H2 here. That's not a metal. This is a list of reactivity series. What? Why is H2, although H2 is on this side of the periodic table, it's not a metal. It's not a metal. So why is it there? Well, because they're trying to do what? Show you the standard cell experiment, sort of. When you start watering down stuff, you start making it incomprehensible. It's a list of metals. That's not a metal. Why is it there? You're saying hydrogen metal is better than it doesn't make any sense. Okay, they're getting it from this table. But here's how you figure this out. Okay? If I combine protons from acids, okay, it's the proton, I'm written here, that's going to get reduced. Okay? And because this table is opposite, we show that the proton can react with all these metals. It's strong enough. This table is reversed. So if this is H plus is getting reduced to make hydrogen gas, all of these metals above it can react with the proton. This is a list of reactivities of metals. These metals are so good at oxidizing that the H plus that's sort of written here, okay, is strong enough to rip electrons. So how do you use this dumb table? I'll say it again, dumb table. The one who's oxidizing has to be above the one who's what? Reducing. It is that simple. So even though you don't see anything there here can reduce, metals don't reduce. Metals don't get negative. So this table is so dumb because if I've got zinc metal, it will spontaneously react with the ions of these guys. Okay? Can you see how crazy that is? So if I was to give you, forget the standard cell now, if I was to give you this reaction, you tell me whether or not this is spontaneous. Let's not do net potentials, okay? What if I give you zinc, 0, okay, plus, let's go copper plus 2, and this would become copper 0 and zinc 0. This would be a single replacement reaction, okay? Using table J, is this spontaneous? Well, who's oxidizing here? The zinc 0. Only metals who are 0 can oxidize. I'm sorry, well, they can't, well, put it this way. The zinc metals that are 0 can only oxidize, they don't become negative. All metals become positively charged. They all lose their negatives. So the zinc is going to oxidize. So on this silly table, where's my zinc? Okay? My silly table, this is my zinc. Is it above the copper? So this is spontaneous. Even though copper isn't reducing, the ion of copper. So the highest one oxidizes, the ion of the other one reduces. Yes?
Wait, so if you go to copper, how come like copper plus 2 electrons gives you 0.34? But if you go like copper plus 2 plus an electron gives you 0.15, then plus another electron gives you 0.5.
Because, well, there's different stability states, and we're going to learn that at a different part of the course. So there's different abilities to lose an electron. We'll get there, but I'm just keeping it simple right now. What if I give you this? What if I said copper 0 and zinc plus 2 makes what? Zinc 0 and copper plus 2. Is this spontaneous? No, because you're going to pick copper, which is below the zinc. It's not as good as oxidizing, okay? How about this? Which metals on this chart, which metals am I going to say here will make hydrogen gas? So if I put lead and hydrochloric acid, what will make hydrogen gas? Lead and hydrochloric acid.
Yes. Yes. Yes.
All of them, okay? Because they're what? It's the flip side of this one. These are all weak enough. These are all strong These are strong at getting oxidized, okay? So it's the well, these guys in H plus make hydrogen gas? No, okay? In AP, you'll get some sort of table, but you should know what we call a reactivity series. Now, what makes this table even worse is they take the nonmetals out. So they give you a list of nonmetals. Now, nonmetals are small. They attract electrons. So this is not metals reactivity is the ability to oxidize. This is the ability to what? Reduce. So look at this list. Who's the best at reducing over here? Fluorine. Okay. And then if you look at, these are called halogens, right? Here's my fluorine. Here's my chlorine. Here's my bromide. Or bromine, sorry. And here's my iodine. Notice it's the same three. Fluorine, chlorine, bromine, iodine. And by the way, as you go down, you get bigger. As you get bigger, it's harder for the protons to attract electrons. That's why the reduction potentials drop. Now, how do you use this table? Instead of using net potentials and keeping the same understanding with positive volts, they flip the rules on you. Okay? Here, the top one is the one who oxidizes. Here, the top one is the one who what? Reduces. So let me give you a classic 100 breaker. This has broken more, this question right here has broken more hundreds, meaning people get one question wrong. I've seen this over the last 25 years come up like 5 times. And if they just gave these students net potentials, they wouldn't get mixed up. So what if I give you this? F2 plus chlorine makes 2 ClF. Is this a spontaneous reaction? Now, if you don't know what's going on here, this is a 0. This is a 0. The front one is always positive, so chlorine in this state has to be positive 1, and fluorine is negative 1. So if F is going to negative 1, that means it's gaining electrons. It's reducing. Oh, that means chlorine, okay, is losing electrons. So clearly electrons are moving this way, correct?
Yeah.
Kind of like acid and base. That's the parallel I have here. So fluorine is getting reduced. Chlorine is getting oxidized. Is fluorine higher than chlorine?
Yes.
This is spontaneous. Okay? The real world would do what? Hey, fluorine has a what? It's higher than the chlorine or the ion of chlorine. We're done. Or if you want to get technical, what's the net potential? 2.87 plus 1.36, you'll get positive volts. Okay, and if I wrote the opposite, F2, I can't do with F because F only becomes negative. So if I do I2 plus Cl2 makes 2 CLI. Hey, I is 0, 0, but I here is negative 1. Chlorine is 0, plus 1, sorry. So this guy got oxidized. This one had to get reduced. Is this spontaneous? Based on table J. Well, iodine's reducing when chlorine needs to reduce. Okay, you see that that's non-spontaneous? But the rest of the world would just use net potentials. I'm sorry, but that's what you're going to have, and I need to throw that at you. Okay, that being said, let's continue. All right, so let's get rid of this. Back to reality, and I want to do a couple of fast demonstrations video-wise. I would be doing these in class, but I just don't have the time. So I'll play my videos and I don't know where my thing is now. Where's my cursor? Cursoring. There we go. Come on, Chromie. Okay, so let's go to, and here's a classic AP problem, regions problem. Which equation represents a spontaneous reaction? If it's table J, metals oxidize. Okay? And so I need a metal that oxidizes higher than the one who reduces. Okay? So that being said, given silly table J, anyone know who is correct? Well, you know that magnesium's pretty reactive. So zinc is pretty reactive. You might not know that calcium is pretty reactive. Okay? And that's okay if you don't know them at the top of your head. Okay? But table J, pull that up here. One day I'll know my alphabet well enough to get these up fast. Here we go. So silly table J. All right. All right, I know you probably have a tough time seeing that, but I feel bad. I'm over it. Okay. So, is calcium higher than barium? Here's calcium, but it's not higher than barium. The one who oxidizes on this list has to be higher. So no. Is cobalt higher than zinc? Cobalt is not higher than zinc. Is iron higher than magnesium? I know for sure. Okay, magnesium is pretty reactive. Okay, and so it's so iron's not higher than that. So we're left with is manganese, Mn, is it higher than nickel? And it is, which means that this will oxidize and the ion of nickel will reduce. But that's all you have for the regions. Okay? Moving forward. Can't stand it, but I had to go over it. Okay. Now, when we drop acid on metals, and this is how I made hydrogen gas, really I'm talking about the proton. And whether using net potentials or table J, we should predict what makes hydrogen. Okay? And I have this reactivity series of metals where I dump acid on different metals and it will parallel this list. Okay? And that's not going to play that for you. But I do want to play the penny demo. Okay? So the penny demo is pretty cool. Okay? And so, and it's a post-1981 penny. Now, what's really cool about the, around 1980, the price of copper shot through the roof. So much so that the actual value of a penny was far greater than the actual federal government's issued 1 cent. So the actual worth of the copper that made the penny, it was like 99.9% copper, okay, far outseated the actual 1 cent. So people were collecting pennies and melting them down and selling them for scrap metals, believe it or not. So they had to make a change. And so what they did is they kept the copper core, but they filled it with zinc, okay? So what I'm doing is taking a penny and I'm just scraping the outside. Now this is an old penny. You can still, by scraping it, I still can see the what? The copper. So this is a 99.9% copper penny. This is a pre-1981 penny, okay? So when I scrape it, it's pure copper, or 99%. Now this is a newer penny, post-1981. To make it cost effective, they filled it with cheap zinc. Has a copper outside, thin layer, but zinc inside. And zinc has a silver color to it. So when I scrape it, I'm going to expose, and you can see the silver color to it. And that, of course, is the zinc. Zinc's got a different color, and eventually I could zoom in there, okay, and you get the point. So what I did with the post-1980, and you can drop an old penny. If you have a penny that's 1980 and drop it or older, it sounds like a thud. And you drop a post-1981 penny, it's like a ting sound, okay? And it's good times. I could do that next period. But in any case, I took the post-1981 penny, and I basically took off the copper sides on both sides, okay? And then I'm going to drop it to hydrochloric acid. Okay, I'm going to stop it here. What do I know? What do I know? Well, party people, okay, why did I do that? Well, the reason why I did that is because I know that zinc and copper have different reactivities than hydrochloric acid. Okay? And what is that reactivity? Is copper spontaneously react with that?
No.
No. I don't know why that's not coming up now. Okay, so just believe me that the net potentials, copper doesn't react with H pluses, but zinc does. So cool enough? Okay, I'm going to play this. Okay, so I'm going to drop this penny in hydrochloric acid at some point. And then I'm showing you at some point the net potentials here. Let's just get to it. And I'm going to give you a break in a second. So I'm just jabber drawing here. But here's the H pluses. Here's the, this is an older table. Copper plus 2. Any case, the net potentials, okay, give you a negative. So let's just put it in. So I'm going to drop the acid onto the copper penny. And on that copper penny, remember, I did what? I took out the copper. I'm exposed the what? Zinc. So when you look at this, okay, and I'll give you a better picture, I think. You're seeing bubblage. What's the bubblage? Right, the zinc being exposed. And I did it on both sides. Okay, so I right here and right here, you see the bubbles. That's where I exposed the zinc. I took the file and I filed away the copper. The copper, or the H plus, can't take electrons from the copper. Can't. It's not a strong enough oxidizing agent. Or in stupid table J, the Cu is below the H2. Or in a real table, okay, the net potentials are negative for copper 0 and H plus. But there you can see the H2 gas I'm making. When that runs for 24 hours, all the zinc 0 becomes aqueous zinc plus 2, and I will have a hollowed out penny. Okay? And I hope none of you guys are FDA, and so when you take it out, I have that hollowed penny. There it is. There was the zinc, and now all I have is a thin shell of copper.
Push it.
And yeah, I'm going to. So I take the post-1901 penny that all of the zinc has been converted to zinc plus 2, and the hydrogen gas is now gone. It's hollowed out. And I'm going to take it. I'm going to show you my strength and my beautiful fingers. Okay? And I'm just going to just show you how strong I am. Okay? And I just can crush it because it's a thin piece of copper foil at this point. Okay? Take your break.
You sell that?
Probably not.
Build that down.